As an example, let us look at the following region. So let's take the area between the circle r equals to 3 sine theta. So we know this is indeed a circle by an exercise. So remember we discussed that r equals to 2 cosine theta was a circle, and I said that you can verify that r equals to 4 sine theta is a circle as well, and this is a circle by a similar argument. So find the area between the circle r equals 3 sine of theta, and the so let's say between the circle with this equation and the cardioid, r equals 1 plus sine theta. And so first let's try to sketch this area between these two curves. So let's say for definiteness we want the area inside the circle outside the cardioid. So these relations inside and outside replace the notions of above and below for the Cartesian system of coordinates. If you look here, this area is inside the blue curve but outside the green curve. So in the polar world we have inside and outside in place of above and below. Okay, so now the sketch. Let's see what we have here. So we have the circle, r equals 3 sine theta. It is a circle centered at 0, 1.5 with radius 1.5, like so. And the cardioid we have already sketched before, and we saw that the cardioid has intercepts 1, let's say 2 and 1 over here, and its rough sketch is as follows. Something like this. And so according to the problem again, we're interested in the area inside the circle and outside the cardioid. So it's important that we have precisely these relations between them, because otherwise we could get a different region. So if we reverse these relations, we would say outside the circle but inside the cardioid, for example, we get this region, but with the present order of prepositions we have inside the circle, so here, outside the cardioid, so like this. This is the area we're interested in. Okay, so to find this area, we would like to determine the values for the angle that correspond to it. So we would like to find the range of angles between these two lines. And so we're looking at this region, which is contained between two different angles theta. So we have some angle here and some angle here. Let's find these angles. So in order to find them, we need to find the points of intersection of the circle and the cardioid, right? Because the points of intersection, this one and this one, give us the values for theta. So let's go ahead and find the points of intersection. It is done in exactly the same way as you would do it for a pair of Cartesian curves. So we just equate the r's. So we say, okay, let's find the points of intersection. We're not specifically interested in points. We'll be content with the angles where these curves intersect. And so, as I said, we would like to equate the two r's. So we have 3 sine theta equals 1 plus sine theta, which means that 2 sine theta equals 1, which means in turn that sine theta must be 1/2. So the solutions of this equation for theta in 0 to pi, so we're only interested in this range for theta because it doesn't make sense to look beyond a single period for the angle. So the solutions are pi over 6 and 5 pi over 6. And so clearly the two angles here are pi over 6 and 5 pi over 6. Great. So now we know the range in which we are supposed to integrate our expression right here. So we are ready to set up the integral. Okay, so we will take this formula and go ahead and plug in our specific information. So we have that area equals the integral from pi over 6 to 5 pi over 6 of 1/2 then outer curve minus the inner curve. So the outer curve, according to this picture and to our conditions, is the circle. The inner curve is the cardioid. So you see that this is the outer curve, is the circle, the cardioid is the inner one. And so we have to subtract from 3 sine theta squared the value of 1 plus sine theta squared d theta. Now, a useful observation to be made at this point in that we have a region which is symmetric with respect to the y-axis. So we have symmetry here. Let's exploit this symmetry. So we can compute only the area contained in the right half of our region, right, and then just double it. So we'll go ahead and only evaluate the area of this part and then multiply it by 2, which means we'll integrate over thetas between pi over 6 and this direction, which corresponds to pi over 2. So this area is equal to 2 times the integral from pi over 6 to pi over 2. And then we have to expand this difference. We have 9 sine squared minus 1 minus 2 sine theta minus sine squared theta. Great. So the 2 will cancel with 1/2, and we'll end up with the integral from pi over 6 to pi over 2 of 8 sine squared theta minus 1 minus 2 sine theta. So let's rearrange them so that we have eight sine squared minus 2 sine minus 1, like so. All right, so how do we evaluate this integral? Well, we can certainly take care of this term and the constant term. So the only issue here is the term quadratic in sine. And to deal with that, we'll use the half-angle formula. So recall that by the half-angle formula, we have that sine squared of theta equals 1/2 1 minus cosine of 2 theta. Substitute this identity into our integral to obtain the following. So we have now 8 times 1/2 1 minus cosine of 2 theta minus 2 sine theta minus 1 d theta, like so. And great, so now it's just a matter of distributing the product and then integrating term by term. So here we'll get four. When multiplying 8 with 1/2, we will get 4 times 1 minus cosine of 2 theta minus 2 sine theta minus 1. And then note that we can simplify further. We can distribute this product again. So we'll get, I'll just write over here. So we'll get 4 times 1, so that's 4, minus 4 times cosine of 2 theta, minus 2 sine theta minus 1. And so I can combine the minus 1 with the 4 to get 3 minus 4 cosine 2 theta minus 2 sine theta. And so this is the integral we can evaluate by integrating each term individually. So let's see what that gives us. We'll obtain 3 theta minus, okay, so the antiderivative of cosine of 2 theta is sine of 2 theta over 2. So if you take the derivative of this expression, it gives you precisely cosine of 2 theta. So I have to subtract 4 of these. And then I have to add as well, I have to subtract 2 of minus cosine theta, because the antiderivative of sine theta is minus cosine theta. And then finally I have to evaluate difference of all of these from pi over 6 to pi over 2. Great. Let's perform the multiplications here. We'll get 3 theta minus 2 sine of 2 theta plus 2 cosine theta. So we can go ahead and evaluate the difference. The first term evaluated at these two values gives us 3 pi over 2 minus pi over 2. So that's 3 times pi over 2 minus 3 times pi over 6. Then minus, then I'll take the difference for, let's put it this way, minus 2, and then I'll evaluate the difference for sine of 2 theta. So I'll have sine of pi, which is 0, minus sine of pi over 3. So that gives me 0 minus sine of pi over 3, so that's root 3 over 2. And finally, I'll have plus 2, then I'll evaluate the difference for cosine theta. For cosine theta at pi over 2 I have 0, then I'll subtract cosine of pi over 6, which is again root 3 over 2. So you see that these two differ only by the sign up front. So I have minus 2, and then this difference in here, plus 2, and then this same difference. So these two expressions will cancel out. And all I have left is 3 pi over 2 minus pi over 2, so that's pi. And so I conclude that my region between these two polar curves has the area of pi. And so in general, this is the approach you have to take when computing such areas. You start by determining the range for theta that you're looking at, as we did right here. Then you write down the integral, and then proceed using the usual integration techniques. And so in general, whenever you can use symmetry the way we did here, for example, you should try to do so.